technical checkup so that we can successfully start the class now. Then. Yes. Mute yourself. Mute yourself. You're not allowed to unmute yourself. Okay. So otherwise, I'll do you mute here. So people are. Okay. So participate in this poll. We'll start in 2 minutes the class. Let all students participate in the technical checkup. Okay. The poll is on your screens. Yes. All of you participate. That's fine. Okay, we'll start with the revision portion. That is from the history of the wavefronts. But first of all, reply all of you. Are you having any doubts? Because one day in between there was like a day for you to revise the things. So are you having any doubt from the ray optics, or from, you can take the doubts from other chapters also, like from the 11th portion also, no issues. But for now, just text the doubts which are from the ray optics. Okay. So I'm waiting for your doubts. I'll give you 4 to 5 minutes, all of you, to reply in the chat box. That if you are having any doubt, ask, we can solve now only, then we'll start the chapter. That is this wave optics. Okay. So your time starts now. You're having 3 to 4 minutes. Okay, so only 2 of the students are having the doubts. Okay, you are having no doubt. Okay, so carry on. Okay, that's fine. I mean, so now I will carry on. So in between, don't ask any doubts now. Okay, I given you enough time to ask the doubts. Okay, good, good, very good. So now we'll start it. So this starts. This is from the history. So let us again watch the movie back. Okay. So what happened in 1637? There was one scientist whose name was Descartes. What he did? He has given his theory of corpuscular theory model of light. What does it says? It says like this, that the light is made up of energy particles. Okay, these are made up of energy particles like this. And then by using this theory, what it did, by using this theory, he was able to explain the reflection process. This was what? This is a reflection process. And next is what? This is reflection process. Okay. We'll not go in the depth of this. We have already seen in the previous class. It will be boring then. Then what? Then after the 1637, there comes the year in the past, 1672 in the history. Then appears a new physicist whose name is Isaac Newton. We know he's known as what? He developed actually the theory of classical mechanics. He's known as the father of what? Classical mechanics. Okay, classical mechanics. Then after this, he used the same theory of corpuscular model of light. He used this theory of corpuscular model of light. I mean, he actually used the modified version. He used which kind of version? The modified version of the corpuscular model of light. He used that. And then he has given the paper, which is named like this, Optics, or a treatise of the reflections, the refractions, and all these things. Okay. So this is all the work the scientists have done in the field of this light and its interaction with the matter. Then in the year 1678 comes the Christian Huygens, who developed the wave theory of light. And in 1801, Thomas Young also did a work by using the same theory of the wave theory of light of Christians Huygens. That is wave theory of light. Okay. And is given the interference experiment via that. Failures of the Newton corpuscular theory. What are the failures? Newton assumed that light travels faster in the denser medium than in the rarer medium, which has been proved wrong actually. Okay. Corpuscular theory of cannot explain the phenomenon of the diffraction, interference, or polarization of light. This also remember. So these were some drawbacks. And after this, we have seen this slide also. See, conclusion was this, at least at the end, that via geometrical optics, it was concluded like this, that light can be assumed to be approximately travel in straight lines. This was assumed by sorry, this is not me. This was assumed by geometrical optics. Okay. That what was the conclusion from the geometrical optics? That in that geometrical optics, we treat it like this, that a light is actually traveling in the straight line. And in the wave optics, the interpretation was this, that a light does not travel in the straight line. Okay. So these are two entities. I mean, these are not, these are against each other, east and west, north and south. Geometrical optics conclude like this. Geometrical optics concludes like this, that the light travels in what kind of thing? It travels in straight line. It travels in a straight line. But wave optics conclude like this, the light does not travel in the straight line. Light does not travel in the straight line. ठीक है? So what's the wave optics conclusion? that a light does not travel in, that a light does not travel, the light does not travel in straight line. Light does not travel in straight line. But what is the geometrical optics conclusion? Its conclusion is this, that the light travels in the straight line. ठीक है? So this is an obstacle in between. So see, this is actually the picture which explains that light does not travel in the straight line. How it is explaining? It's the process is diffraction shown on this picture. What does it says? It says like this. Suppose the rays are going like this. These are the wavefronts, okay? And in between, there is some obstacle been stuck there, okay? So what is happening? The wavefront is getting deviated from the edge. This is what? The wavefronts are getting deviated. So if we say the wavefronts are getting deviated, what does it mean? It means the wave which is associated with this wavefront also get deviated, okay? So we'll say the rays are getting deviated, okay? And when there something is getting deviated from its original path, what is happening? When something is getting deviated from its original path, what does it mean? It means it is no more in the straight line motion, है ना? Because if you want a deviation, you have to break your initial path direction. This is what deviation, some angle. Next is what? So this was the conclusion and can be easily explained by the previous slide. Is it clear? Please reply in the chat box if is it clear. If it is clear. Okay. After this, we'll see Huygens theory now again. So, there's no need of the more of the things. Just see the animation first again, so you can revise because animation gives you the clear, precise picture of the revision things. You know, you can see the circular kind of structures of the vibrations which are generated are here. What the wavefronts, okay, and the side is the wave here. Side is the wave here. These are the wavefronts here. Okay. And the direction here, if you see, these are what? These are passing perpendicular, okay? See, these are the wavefronts, circular kind of wavefronts here. These are the circular kind of wavefronts, and the perpendicular to it are what? The wave direction, okay? I mean, perpendicular to the wavefront shows you how the wave is traveling. That's fine. So see, it says what? Locus of, highlight is this, locus of points which oscillate in same phase is called the wavefront, okay? Locus of the points which oscillate in the same phase is known as what? The wavefronts. And this is the 2D representation shown to you. I hope you have written these things in your notes. And if I draw perpendicular to this concentric circles, which are nothing but the wavefront, that perpendicular will give you the direction of the energy wave. So it's like this. Okay? This perpendicular gives the direction of the energy wave. Next, this perpendicular is nothing. The rate which this radius of the concentric circle is increasing, or you can say the speed which the wavefront is moves outward from the source is called as what? The speed of the wave. Okay, remember this thing always. So this is the speed of the wave. This is nothing but the speed of the wave. Okay. We have also seen in the previous classes the kind of wavefronts are like this. Planar, what kind of wavefronts are like? Circular wavefront, we have seen 2D representation. Okay. Spherical wavefronts we have seen. And we have seen the planar wavefront also. See, इसमें क्या, what is this thing? That if a point source emits the wave uniformly on all directions, then the locus of the points which have the same amplitude are vibrate in the same phase as spheres. See, this theory can be easily been understood by this animation, which is on your screens now. So please be focused. See, this is some source of light, and this curved arrows are showing you the direction of the energy wave. I mean, direction in which the wave is traveling with particular speed, we say. And as this curve arrows are moving further and further, they are increasing in their length in the curved manner. Concentric spheres are being generated, which we can see. These concentric spheres are nothing but what? The spherical wavefront. I hope it's clear. When we say homogeneous and isotropic medium, it means homogeneous means symmetric throughout. Okay. I mean, it's not like this. On one side, it is having the refractive index of, say, some medium N1, and on the other side, it is having refractive index of, say, medium N2. Okay. And isotropic means if you go on all the sides, the dimensions are symmetric. It's same there. Okay. It's not like this. Somewhere it's like, I mean, a circular kind of structure is. See, if you consider the crystal, isotropic by isotropic means what? If you consider the crystal like this, it must be symmetric in all the directions if you go. Okay, na? So similarly, this definition is given about the medium. That if in a medium there is some source of light, these are nothing but the spherical wavefront, spherical wavefront, spherical wavefront, concentric. So as in the 2D, there was circular aperture, circular kind of wavefronts, which are concentric to it. Similarly, in the 3D, this is about the 2D. See, even if you see the 3D picture in a 2D, I mean, if you see the 3D spherical source, a source of light in 3D, that will give you spherical wavefront. And if you see that thing in 2D, you'll get the circular wavefronts. Okay. So these are two kind of wavefronts. Last wavefront is this planar, which is in your syllabus. Planar wavefront. So focus here carefully. It says, let us focus our attention on the small portion on the sphere and consider a plane somewhat like this. So in all of these concentric peripheries, if I extract a small plane like this, having say area ds, 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 students, this will give us the planar wavefront. And the direction of the energy wave will be perpendicular to it. So it will give you plane rays. Okay. So we'll say the rays which are parallel to each other are associated or linked with what? The planar wavefront or plane wavefront. Wavefront. Some says wavefront also. Is it fine? Please reply in the chat box. Please reply in the chat box if this thing is clear. If having any doubt, okay, it's clear. JNV Shimla students, that's fine. Okay, so JNV Roper, Mansa, fine. Okay, cool. Okay. I hope it's clear to all of you, na? Tick. Very good, very good. So after this, Huygens principle. Now we'll go through the Huygens principle. But this also we have seen already. See, these were the 2 points of the Huygens principle. This you have written or not? At least give me a hint. Genuine Shimla students or any other students, please. This you have written or not? Huygens principle definitions. The 2 principles and the definitions written here. Have you written these things in your notes? Please reply in the chat box. I'm waiting. I'm giving you 1 minute, 2 minutes to reply fast. Yes. Okay, so it means you have written this thing. Okay. So see, one more time I'm explaining this to you. Okay. So it's like this. Then we'll directly switch to interference. I'll not waste time here. So in Huygens principle, he told like this: suppose you're having a source of light S, as shown on your screen, and suppose the rays are coming from this source of light like this. These are the rays coming. Okay, and this is the wavefront here. This at time t equals to 0. This is the initial picture of the wavefront. Suppose so. Huygens principle first point says like this: if you consider some points on this wavefronts, if you consider some points on this wavefronts, these points on the wavefronts by themselves will produce a secondary vibration or or like small wavefront, secondary wavelet or some wavefront vibrations. The points on this wavefront will produce in by themselves individually a secondary vibration, which is on your screen now. See, okay, these are the secondary vibrations. Suppose the time it took to travel is like, say, suppose the wave speed is v. So in tau time, it will cover x distance. It means this x will be the radius of this secondary wavefront. If I join the periphery points of this secondary wavefront, I'll get a new wavefront position. See here. So this is a new wavefront position. This is what? New wavefront position. Okay. Okay, fine. So this was all explanation of the Huygens principle. Similarly, by using this principle, he derived the laws. See, no need of derivation. PDF is available to you. But the points to be understood again is this: that he proved this thing which we used in the Snell's laws, numericals, V1 upon V2 is equals to lambda 1 upon lambda 2. He have proved this thing, that at the end he have proved this thing also, that is the laws of reflection. देखो इसमें no need of derivation, just remember the results here. Okay, so yeah, this is somewhat important. Suppose we are having a mirrors. These are among the spherical mirrors now. These are the spherical what mirrors, not lenses, remember. Okay, so these are spherical mirrors, and in the spherical mirrors what happens actually, if you see, it is having the formula, remember, it's 1 minus u equals to 1 by f, isn't it? Is it minus or plus? Can you reply in the chat box? It is minus or plus? Minus is for mirrors or plus is for mirrors? Other will be for lens, that we know already. Reply in the chat box. Okay, I think it's fine. You got it. So this is a concave mirror. This what happens if suppose some rays are okay. You have replied. What is it? It's plus. It's minus or plus. See, two formulas are there. No, one is like this, and one is like this. This is for mirror, or this is for lens, or this is for lens, or this is for mirror. Any one of you. Yes, that's fine. Students, this is for mirror. Okay. And I told you when you use lens, change it with minus sign. So this is for lens. Okay. Just wanted to revise it. So suppose there is a concave mirror, and in front of the concave mirror, the rays are coming parallel like this. You'll be Mansa student, what do you do? Suppose this is a plane mirror, and in front of the plane mirror, what is happening? The rays are coming parallel like this. Okay. So after striking, after getting reflected from the plane mirror, this will merge at what? Which to where it will merge? Say at some point. Okay, say maybe focus, but we'll not consider now. So it will merge like this. But if we see the different picture here, see who is this? Mute yourself. Please mute yourself. Okay. Mute yourself. Okay. So what we'll see? These are the rays coming parallel. Okay. So it will merge like this. But if you want to see, this is a ray diagram shown here. But if you want to see the wavefront picture, what it will, how it will look, it is like this. So we know already, we know this thing. Ki if rays are like this is showing the direction of the wave traveling, energy wave. Okay. So it showed that the wavefront linked with this will be like planar. Okay. So this is shown here. And if you see next, plane wave, this is the incident plane wavefront. And after getting reflected, see when this incident wavefront reaches here, after getting reflected via the concave mirror, it will get reflected like this and it will come like this. This is what? Reflected wavefront. Okay. So AB is the incident wavefront, CD is the reflected wavefront. Similarly, if we use for the convex mirror, again the virtual thing will be made. Hai? So this will appear to meet at the back. It's a virtual image. It's somewhat far behind. This is the virtual image. So this virtual image will be actually acting as a virtual source, which will produce the wavefronts. See what's happening here. So incident wavefront, when it goes near to the convex mirror, a virtual wavefronts are being projected at the back, and this is coming outside of this left hand side of the mirror, which is a reflected thing. Okay. So this is a scene of the wavefront, the wavefront picture in case of convex mirror. Okay, this AB is the incident wavefront, CD is the reflected wavefront. We are actually comparing here, we are here actually analyzing the ray diagrams and the wavefront picture. So after this is a case of lenses. So in the lens, what happens? See, in lens, we know already that if this is a ray picture, parallel rays when passing through the lens will meet at a point on the right hand side. So wavefront picture will be this. This is AB wavefront. When it will reach rear to the optical center, maybe on the side of the lens, when it will pass through this convex lens on the other side, this is a wavefront picture. Okay. Now this is actually biconvex lens. This is biconvex lens. This is biconcave lens. The wavefront picture here will be different. So you can see this is the AB wavefront. It reaches here after getting after getting refracted through this lens. The CD is the reflected wavefront. It's magnified. So there's a difference here. AB is incident wavefront. In both of the cases, CD is the reflected wavefront. AB is incident, CD is the reflected. But if you analyze properly, there is a difference between the wavefront structures. I'm not saying about incident, but reflected wavefront. If you focus here on CD in case of biconvex lens, the CD wavefront, it's curved as compared to the incident. Okay. Plus it's less thin. So it's curved, but it's if you see its height, it's less. You know? Here, if you focus on CD refracted wavefront after getting refracted from this biconcave lens, it's curved, but it's more in aperture. Its aperture is less. If you see the aperture, it's less. Its aperture is more here. Okay. So we say aperture of the CD refracted wavelength is greater in case of biconcave lens as compared to aperture of CD refracted wavefront in case of biconvex lens. Okay. In case of prism, if we see, the things are same. There are not a lot of changes. I mean, this is the AB wavefront. When it will reach on the side, one of the side plane surface of the prism, on the other side, this will give you the CD emergent wavefront or refracted wavefront. Hai na? This is same as the ray diagram. You can see the rays passing like this. It goes from inside. It comes out like this. And let us see the 3D model of this prism. 3D shows you like this. That is the rays going. This is the wavefront. It's a planar wavefront. Remember it. On the other side, it's moving like this. Is also planar wavefront. Okay. So this was all about this a few points about this Huygens principle application or representation of or analyzement of, we can say, like of the ray diagram and the wavefront picture. Now let us switch towards the interference fast. So this is now interference on your screens. Okay. So let us see what are the things we need to study in the interference. What are these things? So these are your objectives, or you can say contents. Okay. So at first we'll go through the introduction to interference. I mean, we'll understand about interference, that what this interference is. I think you reply. Yes, at first we'll understand what is interference. Okay. We'll understand coherent and incoherent source. Okay. We'll see superposition of light waves. We'll see Young's double slit experiment also. Got it. So now first we'll start with the introduction. Write the heading introduction to interference. Any doubts? Anybody's having any doubt, please reply in the chat box. But first of all, before starting the introduction of this interference, I'll go through the animation. First experimental observation, then the theoretical conclusion. Okay. So observe it carefully. See, few things I'm going to tell you here. This is some source of light S1. ठीक? This is some source of light S2. There's a d distance, small d distance gap between these two sources. This complete width is of the screen here. This is a screen which is placed at a distance capital D from the sources. So for first time, this will be switched on. Then after a few seconds, say 2-3 seconds, or maybe 1-2 seconds, second source will be switched on. So they will produce the wavefronts, which are actually 3D spherical, but in the paper pen representation, in the 2D, in the side view, will give you what circular wavefronts. So from after this, S1, S2 will be switched on. So this will also produce the second wavefronts. So these wavefronts will merge and they will give you some different kind of structure. So when the resultant will meet here, it will give you a pattern. This will give you a pattern here on the screen. Okay, that will be alternate bright and dark bands. So ultimately, you'll be able to see like this. You'll see alternate dark and bright bands. Okay. So I hope you're ready for the animation. I'm going to launch it. I'll launch it for maybe 4 times, 3 times. Okay. So focus here carefully. I hope you're able to observe the dark and bright bands on the screen. See on the right hand side, rightmost side. See there. Look there on the rightmost side. Okay. I have launched again. So I hope now you're able to properly observe this thing completely. This is what, this one is what? What is this? This one is dark band. See this dark band. See this dark band. And in between, what is there? In between, there are bright bands. This is bright band. So this is actually the result of this experiment. And why we call it as interference? Because interference is going on. No, see, we see in the natural, I mean, in the common word, we say like this, no, don't interfere. But here it is happening here. What is happening if we see again properly, see this, what is happening? First of all, this is switched on. So then this is switched on again. So now the two circular in the 2D representation or in 3D spherical wavefronts are interfering with each other. That's why these kind of patterns are being made. And when the pattern is taken on the screen, it gives you alternate dark and bright bands. Bright, dark, bright. Is this observation clear to you, students? I hope it's clear. Clear ho gaya na? Okay, so write the definition in the notebook. We'll say like this. This is the definition. The phenomenon of one wave interfering with another and the resulting redistribution of energy in the space around the two sources of disturbance is called the interference of waves. Interference between two waves or more light waves is just an addition or superposition process which results in the new wave pattern. Remember it, okay? I hope it's by itself, it's self-explanatory definition. Very easy, no? Please reply in the chat box if you're having doubt in this. Now, students, let us see the conditions of interference. What are the basic conditions of interference? See, if you want to set a stable and a clear interference pattern, what does it mean? When we say like this, a stable and a clear interference pattern, it means proper, well differentiated, well, like their boundaries must be well differentiated. What? Of what? The alternate bright and dark bands. So when we say alternate dark and bright bands, we mean like this. They must be well visible on the screen. Okay. If you see, this is to set up a stable and clear interference pattern means pattern where? Pattern on the screen. The result, if you want the 100% perfect result, that is well sophisticated, symmetric, well differentiated pattern of alternate dark and bright bands. Like suppose the green color light you are using, so it will be like this. This will give you dark and bright bands like this. It will be many, but I have just drawn the two. Okay. In a particular, I just drawn I took a part of that screen. I shown you the pattern. It must be like this. So if you want students, if you want such kind of pattern on the screen, for this, you have to fulfill two conditions for this experimental procedure. What are these conditions? The conditions are like this, students. First condition is this. The waves which you are using, I mean the source is S1, S2. Usme says the waves which you are using, the wave of light, it must be monochromatic. It means it must have the single wavelength. Why are they saying like this? Suppose, see, single wavelength matlab, if I show you the video again there, see, this both the sources, when switched on, this is what green wavelength, okay. Green color is having some wavelength. We know the visible region is what? VIGYAN. G is for the green. Y is for the yellow. O is for the orange. R is for the red. B is for the blue, I is for the indigo, Y is for the violet. Okay. So here it is explaining us, if we are using this as for green color, okay, I'm in a particular wavelength, use the same for the other two. Okay, the light waves which you're using, you must use of the single wavelength. Otherwise, you'll not get a proper pattern, well differentiated pattern. Because see, we can see it, it's a well differentiated. Black is there. Otherwise, you'll get the mix up of the colors, and maybe you're not able to observe the dark bands there. Okay, so if you want a very better, a very precise picture of this interference pattern, the first condition must be fulfilled precisely, properly. Okay. Next is this: the sources which you're using must be coherent. Now the question arises: what are these coherent sources? And that was also in the content page. I mean, in index page, we've seen this thing. This also we have to study today. Okay. So the sources must be this we understood. Matlab single wave. Remember, there are two kind of wavelengths. Monochromatic in general. Okay, monochromatic, that is having the single wavelength, and similarly you can say dia, tria, but we say polychromatic. Polychromatic matlab, suppose the rainbow rays are there, like rainbow color rays, which is having many different colors. Let me show you. Suppose red color is also there in the light. Suppose, in the DJ and all these things we see. Suppose this is what blue color. Suppose this is what green color. So when the mixing of the colors is there, we say in such a light, we call it as like polychromatic light. Because you can think yourself, it's a common sense. Different wavelengths means what? Each wavelength is corresponding to particular value because it's having different colors. We know the visible region, VIGYAN. It starts from where we can say it's like somewhere like it's 750 nanometers to say some 300, some says 500 like this, so it starts like this. So for different wavelength, the color associated with that wave is also different. So it's a polychromatic thing like this. Now the question arises about the second condition. First is fulfilled, it's understood. The sources must be coherent. Why it's required? Can anyone reply in the chat box? The sources must be coherent, students. Why it is required, the sources to be coherent? See, coherent sources are this. You can see this picture properly. The sources of light which emit waves that have same frequency or zero or constant phase difference. I mean, they must be symmetric. So this is the coherent source. You can see the waves are symmetric in nature. Okay. So such waves or electromagnetic waves which are or light, because light is actually what? Electromagnetic wave, no. So such waves which are originating from such sources are known as coherent light, and such sources are known as coherent sources. Incoherent is what? It's like this. You can see one wave is going like this, other is not symmetric in amplitude also. And if it is, its phase is changed. Phase change matlab, if one is going in this direction, other may be going in this direction. This shows you the phase difference between them is 90 degree. If one is going in up direction, other is going in down direction, this shows you the phase difference between them is 180 degree. Okay. I hope you got the word, understanding of the word phase change. And it says like this: source that emit the waves having the random frequencies and phase difference. Frequency matlab kya? Suppose its frequency is somewhat like this, and some is having the more frequency, keeping all rest conditions as same. Frequency more matlab number of waves in a particular region will be more. Okay. So when you alter frequency and phase differences, you can create a number of waves incoherent, and such a source will be known as incoherent source of light. Okay. Finish. Any doubts, students, please reply in the chat box, because yeah, you can see here the example of the incoherent. So see how different colors light are coming. See, it is incoherent also, it's polychromatic also. Incoherent and polychromatic. What you didn't understood, please reply. Okay, through the picture you will get it. Okay, don't worry. Please focus on this picture. This light source lamp is emitting different color kind of wavefronts. So we'll call it different colors. Matlab each color is associated with different wavelength. Are wo pattern, you have seen this pattern, no? VIGYAN. each color different wavelength. So it's a polychromatic plus incoherent. Matlab everything is not symmetric. Just consider the simple sense, not symmetric. When passing through the pinhole, it gets coherent, matlab symmetric, but still it's polychromatic. Why? Because different colors are there. But when it's been passed via or through the wavelength filter, now it's symmetric also, very much symmetric, plus only one color light is coming. It means what? It's a monochromatic coherent now. These waves are now monochromatic plus coherent. Is this clear now? Please reply in the chat box. Okay. The time is up, students. So that was all about the today's class. I have given many number of times, so I'm giving here again. This is our WhatsApp number. If you're having any doubt, you can text. Or if you feel you need some counseling kind of thing, ki, sir, I mean, what about JEE and like how to attend the paper? And what about the other exams like we can give and all these things? If you want the counseling about this, if you want to know more about IT, JEE, NEET, or if you're having some personal doubts related to physics or what you need to do after 12th, so you can reply or call here. I mean, you can text here or call. Okay, no issues. So this was all about today's class, students. In the next class, we'll see some questions, we'll see some conditions. On theory of interference, we'll derive an equation of interference, and then we'll see the constructive interference and conditions for that, and we'll see destructive interference and the conditions for that. Okay, so that is all about today's class. Next class we'll see all these things. So I'm going to end the class now, students. If anybody is still facing any doubt, please reply in that chat box. You're having still few minutes left. 5 minutes are there. Okay, I have launched the poll for you. Please, remaining students, please participate in this NPS. It is available on your screens. Please reply here. If you're having any doubt, if you're facing any doubt, please reply. Otherwise, we can end the class. Okay. So bye-bye all of the YouTube students. Okay. Bye everyone. We'll meet in the next class. So for reference material, as I've told in the previous classes also,